So today I'm going to talk about some of the real world use cases of AI and where they're basically applied in use case like use cases that are already out there, and we are basically kind of interacting with this kind of AI. Uh, so some of that is about the kind of smart city applications, and the rest is about IoT. That deep learning and machine learning are kind of kind of connecting somehow with those devices out there in the field. So last time I basically talked about this because we are all developers, and it's actually quite interesting to see like the Pope kind of writing a piece of code. So that basically shows the power of developers and how important coding has become for children, for schools, for societies, and even prominent figures like the Pope actually is promoting technology, which is a great thing. And we if you look at what used to happen hundreds of years ago, we'd never had this. But this was actually quite interesting because it was promoting technology to women in technology and female in technology. Um, so just a little bit about myself. My life is all about developers. So I run a team of developers, multiple teams of developers across Europe. And what we do is we engage developers in a meaningful way. We try to promote technology and kind of sit down with developers, help them create innovation and also promote technology for good causes. And this is quite rewarding. And at the same time, we help startups. Some of the startups are looking for ways to integrate AI and machine learning into their applications. And because IBM is actually quite good at that, we try to kind of simplify that process for startups and developers. As you can see, the photo in the middle, that's my team in the UK, in London. But we've got teams across, different cities and countries in Europe. We've got in Italy, we've got in Germany, Amsterdam, Tel Aviv, you name it. So I like to start my talk with a little bit of overview about artificial intelligence and what AI is, and how AI basically kind of works as an umbrella for deep learning and machine learning. And these terms are interconnected, they overlap in a lot of areas, but there is still a lot of confusion around them. Many people kind of use AI, machine learning and deep learning kind of interchangeably, which is not actually the right way of kind of promoting important terms. But before I kind of go deeper into the use cases of AI, I like to kind of clarify each one of those. When we talk about artificial intelligence, that's just an umbrella for any kind of attempt to mimic human kind of behavior. So, for instance, some people have a description for AI, like John McCarthy. So they talk about it on a very high level. But then when we go a little bit deeper, like machine learning, it could be a little bit more technical. So when we throw massive amounts of data at an algorithm and we expect some sort of certain output, that's where machine learning is. So we are basically giving the experience to machine learning. But then when we talk about deep learning, it's a little bit different. We are basically asking the system to learn from those experiences and kind of create its own perception of what's actually happening. So instead of data, we are basically feeding experiences. That has kind of led into a lot of developments and evolutions over the past few years. I wouldn't say it's been few decades, but I'm going to get into the historical timeline of how AI, machine learning, and deep learning have kind of evolved. For developers, we can actually look at it this way. If you're talking about machine learning, we are talking about input, feature extraction, which we all need to do that. And then those features need to be fed into the classification part of our algorithm, and then we expect some sort of output. But then when we talk about deep learning, all that data goes into a neural network, and that's like a black box. So we've got no control over that, let's say, in a loosely way, kind of if you wanted to kind of describe it that way. And the output is kind of unexpected, but we can learn from that output and kind of verify whether that's what we are expecting. So we use software tools to build a foundation of logic and build a foundation of data sets that kind of sits on top of that logic. So that's the best way of kind of describing it. So when we move into the area of deep learning, it gets a little bit more complex. It's basically, it's about the way the algorithms are looking at the experiences of data and data. That's the way we can kind of, define it. But then it's about human and a machine together. So if you look at the human side, we've got goals, common sense, value judgment. That's based on our own perception. But then when we talk about the machine, it's about math, pattern discovery, and statistical reasoning. So in order to have a good system in place, we've got to put these two pieces together if we want to have a reliable system. We can't really kind of focus on one and ignore the other. And in IBM, that's the way we're trying to do. We are trying to kind of amplify, or let's say boost the decision-making process by bringing the machine intelligence into the decision-making process done by humans. We are not saying that the machines can replace humans. We are saying their perception, their kind of recommendations should be taken into account. So, for instance, you've come across Watson. You've heard about Watson. Watson's been kind of the core of IBM in AI and machine learning and deep learning, and Watson in general is basically about kind of boosting that decision-making process. So looking at the historical timeline, artificial intelligence started a little bit before 1980s. It kind of came on a long way. It was basically the kind of to perform activities. It was basically focused on that and kind of predictions within specific domains. That was the purpose. But then once we came a little bit further, around 2000, we are basically creating systems that, cognitive systems that's like, deep learning, that the systems are learning from those experiences and they're behaving in somehow unexpected ways. And that's basically going from weak AI to machine learning, and obviously further that is deep learning. And again, if you look at when CNN started, that was a little bit before 1990s, and CNN is convolutional neural networks is actually the base of most of the AI processes that we are dealing with every day. And I'm going to give you, kind of show you some of the use cases, like footages of videos, like you can actually see how systems are predicting and kind of recognizing patterns and images. And then furthermore, as I said, in 2000, we started looking at deep learning seriously. So let's look at what machine learning is. So machine learning basically approaches problem solving differently. So let's say we build a robot, and the robot is supposed to, open a door, pull a door open. So obviously, we can easily say, here's the robot, walks up to the door, and then opens the door. What if we have a different kind of door? What if the door needs to be pushed? What if the door is kind of sliding up? So the way we can actually do that is kind of, by showing the robot multiple or, several thousands of, different doors and in how they basically can open. And then the robot can learn from that. So instead of us kind of programming the robot to do that job, kind of a multi-step way, we can actually teach the robot how to deal with different kinds of doors. So that's kind of the best example of machine learning. So, for instance, if you look at this handwriting, obviously you all recognize that, but how? That's the question. It's quite simple for us. It's because we've seen lots of photos, we've seen lots of different kinds of handwritings, and for us it's actually quite simple to recognize that pattern. But then for machines, it's just a grayscale image, and it's kind of taking each pixel and kind of flatten that into a one-dimensional matrix. And then by kind of tagging initially this data, we could basically say this is number 1, and how the machine can easily look at it and say, hey, that's number 1. So I'm basically going to segue from here into the most important application of machine learning and deep learning, which is image recognition. So if you look at it from the mathematical point of view, this is just a softmax or logistic regression, and it's just again the same process, applying weights to each pixel and then kind of getting the output from that. Is it simple? Not really. In order to answer that, whether it's that simple or complex, we've got to look at where the AI is used today. So we can basically, by having an overview of how the industries are evolving, 60% of businesses already have ML strategy, which is awesome. 1/3 of them have they're actually in a mature stage of applying ML. And 50%, half of them actually have already some sort of return on investment process, kind of model in place. So they're looking at AI as a way to generate profit. They're going into different segments of industries with different verticals, but it really annoys me to kind of categorize all these applications based on kind of their industry. I think most of them can be easily mixed and matched according to your application. But manufacturing has completely evolved with AI, and I would say hospitality as well. If you look at the way social media is working, we are getting all that input and kind of optimizing the process. And also healthcare. Healthcare, I think, is another important part that we have seen massive investment in terms of kind of for curing cancer and prevention. So just very briefly, how to spot opportunities, where you can actually use AI. If you're collecting data in one form or another, and you can actually change that, like let's say, instead of filling a form, you basically use voice recognition to get that input, or kind of using visual recognition to scan documents and automatically get that input from your customers, from your clients. That's one area you can easily say you've got opportunities for AI. If you've got like some tedious business processes that you can actually AI can help you to optimize that, that's another one. So there are many kind of processes that companies are dealing with, and they're basically very routines, and you can easily have machine learning to replace that. And the third one is where you can actually delight your customers. So instead of them trying to search for something, like let's say on Netflix, all those recommendations coming to you based on the history of watching some series or movies, if you can make those recommendations in a smart way, then you're actually delighting your clients and customers, and that's where you can actually have AI helping your business. But again, going back to applying visual recognition, medical imaging, satellite imaging, inspection, insurance, those are all the areas that AI can help you a lot. And those applications are already in place, so you can actually see things happening. So I'm going to give you a very quick example. Like when you look at bank robberies, like those movies involving bank robberies, you always have that kind of hero, employee who tries to call 911 or press that alert or alarm or something like that. But these days you don't even need to have that one. So the system can easily recognize people and different objects and different behavior. So this is a real footage where AI was applied, and as you can see, as soon as the thief basically walks into the bank, the system recognized that there is a gun involved, they're like shooting, and all that basically led into kind of triggering an alarm. So nobody needs to do that anymore. The system automatically triggers that alarm. And if we go to, like, let's say, for instance, in for shopping, there's been massive kind of amount of thefts for supermarkets. Where can you apply these kind of machine learning systems that basically detects any abnormal behavior, where that particular object, that particular product had to be scanned, and basically the one doing that decided not to, and the system can recognize that. So if you look at this footage now, this one has been scanned properly, but there is a process at some point that one object kind of I think it's the next object. Yep, that's the one. No. So all those objects, all those items are being scanned, and then interesting. I think that was one of the first ones. probably was in the, oh yeah, that's the one. So as you can see, kind of, try to not to scan it. So it went under the table. So that's where the system detected, kind of scan avoidance. And another one is kind of, drone surveillance. So that's the part I did a lot of research before. And as you can see, the behaviors, the kind of people walking around, and the kind of objects like the cars are being properly scanned by a drone, and that can happen automatically, autonomously. You don't need to have someone kind of sitting at a desk, with multiple cameras doing all that things for you. So that can be done automatically by the system. And another one, which is quite interesting, is about kind of monitoring kind of a smarter and safer cities. How can we actually create a smarter and safer cities? So if you had looked at that, it was like a near miss. That guy who's walking, the pedestrian, it was very close to that car. So the system can recognize that, and they can basically do something to avoid that in the future. So by having all those kind of multiple warnings or alarms in place, you can improve the streets. The same goes for parking. Like, how can you actually optimize the parking space in one area? And these are actually real footages of videos basically taken and AI applied immediately on them. So it's instant. Urban planning is another one. If the cars and different types of vehicles can be recognized by cameras, that's another system that we could basically say how much traffic is coming to the city. And I think for Italy in particular, that's quite interesting, because I was just like, when we were driving to the venue today, I was like, wow, look at the, how narrow the streets are, and at the same time, you've got the fastest cars in the world. So I was like, wow, this is awesome, because you can't really do it here. I mean, only movies, I would say. So. Looking at that, it sounds a little bit complex, maybe, how to create those systems, the ones that I've just shown you. Kind of connecting those cameras, creating those models. You don't even need to do that. It's very simple. Like, if I want to talk about IBM or any other kind of competitors, we have, all these big corporates have made this process very simple for developers to integrate this kind of intelligence into your applications. And I'm going to show you how this can be done in less than 2-3 minutes, basically. And the secret to that one is basically APIs. So you kind of get on a structured and a structured data, you push it into the server in cloud, and you get the insight. And based on that insight, you can make decisions. So APIs and platforms. You've got Google, you've got Microsoft, you've got AWS, Amazon Web Services, and you've got IBM. You all offer the same sort of services. There's no difference in them whatsoever. Maybe some are better than others in some areas. Like, for instance, IBM is really good at health recognition, like when you have patents for cancer or some sort of kind of medical problems. Some others are really good with customers' data, like Google, because of all that data they've got from emails and kind of interactions. But how you do it? You basically create a service, retrieve a credential, and then basically you call that endpoint with your data. So you feed your data, and you get the results back. If I talk about IBM, we've got different kinds of services: discovery, conversation, empathy. So you can have a tone analyzer. So you could have a microphone connected to a Raspberry Pi. You capture a little bit of voice, send it to the server, and then you can actually look for stress in somebody's voice. Or you can look for some sort of pattern in somebody's voice, like so simple. Or if you want to create a chatbot, you feed that data into the server, and you get a result back. And all you need to do is like 2-3 APIs. So I'm gonna show you a quick demo, exactly the same thing that you've just witnessed in in those footages. So looking at this, so this is Power AI Vision Object Detection. So if you want to create a data set, if you want to kind of you basically add your data set, which could be the images, photos of soft drinks. You upload them into the server, and then you start tagging that data. So this is a Diet Coke. That's kind of a Sprite. That's another type of soft drink. And then if you have multiple photos of the same thing, so the system can learn from that and knows exactly which type is which, and then you can easily assign those tags to those images. So that's labeling basically. It's quite simple. Anyone can do that. So you don't need to be a kind of a pro programmer, like kind of expert programmer in machine learning or deep learning. This is something that can be done using this graphical user interface. The same goes for this. We've done the same process with cats, with dogs, kind of different species, to find out, how they work. Then you need to augment data. So that's basically kind of, correlating that data. And so now we are basically creating a model. So let's see. The only reason I'm not doing it live, because every time it fails, like, the gods of demos. So I decided to record everything and just play it. So now, we need to train it. So you've got your data set that you've labeled, and now you're basically feeding your data into the system to build a model. Because it is done in cloud, and we've got massive power behind that cloud service. If you do it on your computer, that would basically take a little bit longer, depending on how much data you're basically throwing at your computer. If you've got a massive GPU, then fantastic. But then this process makes it much easier, and is in most cases free. You don't even need to do that. Then you need to create your REST API, where you can actually say, this is my data, give me the results. What sort of kind of image is that, the one I've sent you? Now we are testing. So as you can see, the system recognized that's a Diet Coke, and the confidence value is kind of around 100%. So you see, it was quite simple. So we created a data set, we built the model, and then we created API. So that API, if I go back here, so that was the API was given to me, the URL. And that URL can be integrated into your application, into your Raspberry Pi, your computer, or whatever have you. And then once you have that, it's just a matter of feeding that data into that URL and get the results back. You can do it in Python, you can do it in Java, JavaScript, Node, whatever you have. So now I'm going to tell you how we've actually done the same thing in my previous job. I used to work as a research scientist at Intel before I moved to IBM. At Intel, we had a massive project at hand. So we wanted to create a kind of a platform, a fabric for research, where we could have different areas of AI integrated into smart city applications. So we started with Billion Device Challenge. And for that, we picked Queen Elizabeth Olympic Park. That's one of the largest parks in actually London. I think it's the biggest park in London. And that's where the Olympics happened, basically, back in 2012. So it was like a mini city within a city, because we had residential areas, we had rivers, we had sport venues, we've got a shopping center, massive one. And that's a perfect scenario where you want to kind of test out different scenarios. But it's in a controlled environment. And again, there are multiple kind of benefits for the mayor's office, because they wanted to get people into the park. After the Olympics finished, basically people kind of started not going there, stopped going into the park. So they wanted to get people into the park and kind of showcase different kind of technologies there. So one of the things we wanted to do was having multiple kind of overlapping communication platforms. So you've got cellular communication, low power wide area network, Wi-Fi, mesh, you name it. And for that, we decided to go with the orbit. So there is this amazing tower in London, in the Olympic Park. It's called the Orbit, and is basically we managed to install a receiver on top of the Orbit, which is basically about 114 meters and above the ground, And we put this LoRa receiver. LoRa is a technology that allows you to capture data in the vicinity of about 20 kilometers. It's really good, it's really powerful, and it's quite cheap. So we put a receiver there, and using LoRa, we wanted to capture data from different sensors in the park. So what we did, we created some boxes with multiple kinds of radios, Wi-Fi, BLE, LoRa, 15.4, which is like Zigbee and Z-Wave. So we created those boxes, and then we installed them on the lamppost. And these boxes, they were capturing microclimate data, water quality data. Some of them, they were quite close to the river, and bat species. That's the most important one. You're going like, bats? I mean, are you kidding me? Well, actually, bats are very good indications of biodiversity of an environment. So that's where the ecologists told us, can you actually start capturing bats' voices or kind of calls? And I was like, seriously? And they were like, yeah, they're like humans. They have stress calls, social calls, you name it, exactly like us. So by capturing that data, they could say whether those environments, like those different parts of the parks, are actually good enough in terms of the biodiversity. So we started capturing data. So we had sensors around the park, and then we had that kind of orbit where we had the receiver. A single receiver was enough for the entire park, and we were even capturing data from the other side of London. I installed that receiver myself. That was before Prince Harry, took his first slide down. So that was like when the park was kind of, that slide launched. And we had a gateway. So gateway was that receiver on top of orbit, and all the sensors were sending data. And through REST APIs, we started analyzing data. See, how the data actually differ. So I can show you, this is a simulation of the kind of data we were capturing from the park based on real data that was coming. So we were capturing 400, 500, pieces of data per second. So it was massive. And in terms of the bat calls, we were capturing a gig of data per second. So just imagine, that's massive amounts of data. Some of that data, from the sensors, were coming from through BLE. Some of them were coming from Wi-Fi. Those gig of data from the bat sensors. And what we wanted to do was using machine learning to optimize latency, throughput, energy, data rate, all those things for the sensors. And in that way, we wanted to optimize the way the network works and prolong the lives of all these small sensors. So in edge processing, the sort of operations you do is sorting, aggregation, duplicate data elimination, and you name it. And then we looked at the anomaly detection, how could we have multiple streams of data coming into the system, and this basically shows you. And then we basically tag where we have anomalies. Those are unexpected behavior, unexpected data. But that need to happen, on a real-time basis, which is really, really difficult to do it in the field. So in Internet of Things, you usually have silo only, edge only, and edge and cloud. So you either do it on the sensor, you do it in the field using a gateway, like edge processing, or you do it in a hybrid way. You do some part of that aggregation or processing in the field, and some of that in the cloud. And then you can combine them to make meaningful data. So the good news is by 2020, there's going to be 50 billion devices, and that number is changing all the time. This is based on Gartner analysis. If I want to talk about edge computing, the most important piece about edge computing is about bringing down that latency. So let's say when we capture that 1 gig of data from the bat sensors, if we wanted to send it to the cloud and then get the results back, that would have made a massive delay between capturing, processing, and then getting the results back if you want to take actions immediately. So latency is very important, so that's why edge computing is very important, to do the processing in the field. And APIs are actually quite good at that, because the same process that I explained to you before, you could do all that image processing in the cloud. You can actually bring it down into your edge device. And the second one is the transfer cost. When we talk about the park, in the park they're like a stadium. And every Sunday there was a game. West Ham United, they have their stadium basically in the park. So every time there was a game, there was massive amount of traffic, noise coming from the mobile cell phones basically. They all operate on 2.4 gig. and we had massive amounts of noise. So it was really hard for our sensors to send data up to the cloud, to the receiver. So we had to switch channels. So our boxes became quite smart to switch radio based on the noise level. And that's basically sometimes can help you to transfer costs. If you look at the noise in the environment and how much data you need to send or receive, then your system can easily adapt. And the same process basically happens in manufacturing and different verticals. They've got the edge computer and they've got the analytics on the other side. So do you want to do it on a computer, or do you want to do it like on a small gateway like that? Obviously, you're going to go for a gateway. You can't really put a computer or a laptop in the field. Some of the applications of neural networks that are currently running on boxes like that, because most of them, they have Linux. And you can easily run that. So you could have CNN, RNN, all those kind of, processes that you have for machine learning and deep learning even. You can easily run them on those gateways. And that's basically taking us from the biological neural network to artificial neural network. I don't want to go into details of that and how those basically, how AI basically works in that way. But let's say if you want to have a Raspberry Pi or a mobile phone in the field, how do you do that? You can easily have TensorFlow Lite. That's another one from Google. So they've got this amazing runtime that you can put it on your Raspberry Pi or your mobile phone and put it out in the field. So using the APIs either from IBM, Microsoft, or another company, but at the same time you could have it running in the field on those small devices. It could be a BeagleBone, a Raspberry Pi Zero even, and that basically does the same job that I've just shown you on the cloud. And sometimes a CPU isn't enough, so you want to have a GPU in the field. Again, there are many cons and pros. You could basically have a small number of cores, but in GPUs, you've got massive number of cores. And it's actually getting better and better every day. So if you look at, for instance, NVIDIA, they've recently created this amazing platform, Jetson TX, and they've got actually a newer platform out there with 515 meg of RAM, and basically what that does is just a small kind of credit card size device, and that's less than $200 basically, and it does the same job that you run on your computer. So if you do all your model, if you build your model beforehand, you can easily feed your data into this small device and get the same results. If you go for something like beefier, like Xavier, this is awesome. It's got like multiple CPUs, multiple GPUs, and you can do a lot of good things with this. A robot can easily run on top of this device, and it's just this small. You can use smart open source frameworks, Keras, TensorFlow, you name it. And the other option for you is actually using IoT platform, Watson IoT platform in the cloud. And that basically makes it quite fast and reliable to send your data up to the cloud and get your analytics back. Products and services, maximizing operational efficiencies, you name it. Those are the good things for big businesses. And then obviously when you look at IBM as a portfolio, IBM is quite kind of reliable as a platform, because all these big banks and big companies are putting their platform, are putting their data on top of IBM to get the best out of what they have. So I'm going to, since I've got a little bit of time left, this is how Watson IoT platform basically works. You've got your gateways, you've got something in the middle, which is the APIs, blockchain, analytics, connection services, you name it. You could have everything in the middle, and then your dashboard and solutions could be on the other side. And it's, again, as simple as calling that API that I just shown you in that clip. Again, different verticals. We've got good success stories. L'Oreal, Rotterdam, they're using that for tracking ships, and you can even have it for mining purposes. So these are real applications today. And obviously, IoT platform in IBM is actually kind of it's got this massive backbone of all these open source organizations and companies, and you can have it in public cloud, private cloud, or hybrid, somewhere in the middle. Now, I'm going to very quickly tell you about some of our great resources for you. So if you are a developer, you want to start kind of exploring and creating some of those solutions. If you go on developer.ibm.com, you can get a number of code patterns. Those are recipes. You can create a solution from scratch, and each one of them basically they're about 100 solutions, and they're super simple. In less than kind of 30 minutes, 40 minutes, you can create a solution, and it doesn't need to be IBM only, by the way. It's basically showing you how to create solutions. Any one of them, you can actually create them, include them into your applications. And the good thing about them, they are basically patterns. They're showing you the flow of data between different components. And we have how-to guides, we have open projects, and you can combine them together. So for instance, if you look at some of those code patterns, like detect, track, and count cars in a video. Super simple. Track donations with blockchain. That can be done in less than 30 minutes. Again, you don't need to use IBM platform. It's basically about the education, how to create solutions in a kind of a structured way. For IoT and blockchain and machine learning, we've got some interesting ones in the way that I've just described it to you, creating APIs, integrating them into your applications. The last part that I'm going to tell you today is about Call for Code. So we've got this amazing challenge with Clinton Foundation, with American Red Cross, Linux Foundation, and United Nations Human Rights Group, basically. And our challenge is for developers to create solutions for natural disaster, whether before or after. And if you can submit a solution and you win, you're basically going to get $200,000, award. And last year, actually, Project OWL won that challenge, and basically we supported them throughout the process to get VC funding to deploy their solutions out in Puerto Rico, for floods and etc. So again, this is a very amazing kind of initiative for developers to contribute to some of the great causes out there. So and IBM is not benefiting from that anyhow. It's just us basically being part of this amazing initiative. So I really encourage you, if you've got a solution, if you want to actually team up and do something, please go on callforcode.org and submit your solution. So that's Project OWL. Last year we had more than 100,000 developers participating in the process, and I was actually in San Francisco with the winning team celebrating that. It was great. So Project OWL basically used the same kind of IoT devices out in rivers to kind of capture data about flood and kind of natural disasters. And we had also runner-ups who kind of get a lot of support from VCs and accelerators. So as you can see, some of those links, developer.ibm.com/call4code, or if you want to become a supporter, that's also the way of doing that if you're a company. Again, it was quite good and rewarding to be part of this. Last year, I traveled around the world attending different hackathons. We've got a hackathon coming up on the 21st of June in Milan. So please check IBM website to make sure that you attend that one and submit some solutions, and you can even participate in the process. That's all. Thank you.
Any questions?
No way. I always get a lot of questions. Cool.
It was all clear.
I think somebody.
I saw that you used the LoRaWAN as a technology, but I think you should know that it's very limited because basically it's more directional. We can send only data and a bunch of bytes depending on the spread factor.
Absolutely.
And also for getting information from the LoRaWAN, it's quite tricky because there are some standards like maximum 10 times downlinks per day. So how do you use LoRaWAN on this kind of scenario?
So basically those limitations on Sigfox, LoRaWAN, they all have it because of the European regulations that you can only use 10% of the bandwidth. But obviously that's the only solution out there at the moment, something on a low energy, low cost. That's the only thing out there. I think 110 messages per day, I think that's more than enough, to be honest, in my view, based on those applications that we run in the park. Alternatively, you can have 802.15.4 in a Zigbee way to kind of mesh network, but that comes with a lot of cost. So it's all about, on the LoRa side, if you adjust your spreading factor and data rate properly, I think that 110 messages per day is going to be more than enough. Because if you're dealing, let's say, with kind of water quality changes on the sensors that are available out there, you can only see those changes every hour, probably every 2-3 hours. if you're dealing with air quality, that's the same thing. You don't need to have that high frequency. Temperature, maybe you can actually have it like every 5 minutes or every 10 minutes, but you can only trigger the system when there's some sort of, kind of interesting event happening. So our boxes were, quite smart enough to not send data when, there wasn't a massive change in, let's say, temperature or humidity, and only send the aggregation of that every hour. And that was like a single message for all the parameters. And I think that was actually quite good because you get about, 5 to 10 messages per hour. And I think for any kind of data out there, that's actually good enough. But if you want to have more than that, obviously you can use Wi-Fi. But then you have to have, power out in the field, which is very difficult these days. Other alternatives, Bluetooth, for instance, you can send Bluetooth data. So one of the things we basically tried, I didn't talk about it. So when people walk in the park, if they download the application for the park, those sensors are able to relay data through their mobile phones to the network. So they're walking by, and their phones are capturing that data and sending it through Wi-Fi or their cellular communication. And in return for that, they get some sort of rewards for walking around the park. And we were actually encouraging people to go for a run around the park to capture that data. So there are many, many ways. But at the moment, LoRa, in my view, is one of the best way in terms of the range, in terms of the power consumption, and the fact that you don't need to have cellular towers like Sigfox, where they have to have base stations. You can easily run, deploy your network as you like. And I think that level of freedom is actually quite good. Otherwise, you've got to go for Sigfox, and Sigfox is quite expensive sometimes, depending on what sort of plan you get. And also, you need to have a coverage. So if your area doesn't have coverage for Sigfox, then you're in trouble.
Yeah, more gateways.
Yeah, exactly. Yeah, that's the thing. Yeah.
Thanks.
Right. Welcome. Awesome. I knew that.
Again about LoRaWAN, which was actually the distance you managed to get message through in your experience? Just
So
real field experience.
True. So theoretically, 22 kilometers based on the papers in the field. Don't quote me on anything. It was about 12 to 13 kilometers. But for the park, it was more than enough because the park was about 2 kilometers by 4 kilometers. So it was more than enough. But again, it depends on how you adjust your spreading factor, baud rate, data rate, coding, the channels. There are many, many factors in place. So I basically created a box, walked around the park to get the noise level, SNR. You've got to adjust your SNR as well. So it's really difficult, how to. But theoretically, the way they've done it is like line of sight in vacuum, and they've got over 20-something kilometers.
But you reached like 3 kilometers in East London.
Oh, absolutely. 4 kilometers, 5 kilometers, easily. No problem whatsoever. I think it was on a spreading factor 12, if I'm not mistaken. Yeah, it was on 12, yeah. Yeah, worst one, yeah. We could say worst one. Yeah, something like that. But again, your coding rate, you need to adjust that one as well. So, cool. We've got a lot of LoRa developers here. Awesome. I think Italy is actually quite interesting because you've got, on the IoT side, I've seen a lot of interest here with different kind of technologies and the fact that Arduino is coming from Italy, so which is awesome. Cool. Yay.
Are you using the Things network for collecting data?
My friends are. So we are working with Digital Catapult in London, and Digital Catapult got the Things network and an antenna on top of their building. It's working very well. So it's an alternative if you want to rely on someone else rather than creating or putting your receiver out there. But I've got my own receiver in my terrace in London. I'm receiving lots of data. Seriously, like some interesting data. People are saying like, 102 like SOS. So I don't know who's sending that, but it's funny. It's not coming from a space for sure.
Thanks.
All right. That's it.
Okay. We're done. Thank you very much, Mo.
Cheers. Thank you.